Thank you. All right, no more submissions. All right, the deadline is already 3 o'clock. I'm not going to accept any more submissions. Are you guys okay? How come there are so few people coming? They don't like my lectures or what? Yeah? Come on, guys, take a seat. Take a seat, guys, please. Shh. All right. Good afternoon. I mean, as I said last week, I would really appreciate if you could hand in your quiz early as possible. You know, I mean, it seems, I mean, nobody in the university actually marks nearly 400 papers every week and sends you emails, right, attaching your quiz, right? Nobody does that. And I'm doing it because I do care for you guys. I spend a lot of hours doing this for you. So I would really appreciate if you could hand in your work as early as you can, right? Okay. Now quiz 6 is due next Monday. Quiz 6 is also based on stuff we did last week. Now what we're going to do today or this week is about maximum likelihood estimation, which I briefly introduced last week. I talked very briefly about maximum likelihood estimation. Right? I mean, maximum likelihood estimation is a method for constructing point estimators. I mean, all of you know what a point estimator is by now, right? A point estimator of a parameter theta. You can have more than one point estimators, and you can decide on the better one by choosing criteria like bias and MSE, right? That's the stuff we covered last week. Now this week we're going to talk about ML estimation for how to create or how to construct point estimators, right? So this is what I did last Thursday. And this is some more of the stuff I did last Thursday. So if you have a random sample from a PDF f x with parameter theta, this is the procedure. This is the procedure to follow in order to find the maximum likelihood estimator, right? It's a 4-step procedure. The first step is to write down the likelihood function, which is the product of the density functions. The second step is to take the log of the likelihood function, which is if you take the log of the sum, you get the sum of the logs. Some of you did not seem to know that last week. I mean, these are pretty, I mean, if you take the log of a product, you get the sum of the logs, right? That's a simple basic fact in algebra, right? And the third step is to differentiate the log likelihood function with respect to theta and set that to 0. Let theta hat denote the solution of this equation, right? And the fourth and the final step is if the second derivative of the log likelihood at theta hat, theta equal to theta hat, if it is a negative number, then you can say that the theta hat is a maximum likelihood estimator of theta. All right, guys? So it's a simple procedure. And in this procedure, I have obviously assumed that these are continuous data. So I've assumed implicitly that the data that we have here are continuous data following a continuous distribution. Now what happens in the discrete case? That's what I'm going to talk next. Now if you have discrete data, You do the following. Okay, so suppose you have data from a discrete distribution with PMF, probability mass function, P x semicolon theta. So theta is the parameter, right? So I'm implicitly assuming these are so theta is the parameter. All right, now in this case, the procedure for finding the maximum likelihood estimator is as follows. Step 1, step 1 is you define the likelihood function as the product of the probability mass function at xi, I from 1 to n, right? Okay. Step 2, take the log of the likelihood. So log of L theta right, so if you take the log of the likelihood, you get, once again, log of the product is the sum of the logs. Remember that, right? Okay. Step 3, WRT for with respect to, I'm sure you know this notation, WRT. So you get the following equation. Equal to 0. And let me call this equation star. Right? And let, you guys okay? Let theta hat denote denote the solution of star, right? And step 4, which is the final step, if the second order derivative at theta equal to theta hat is negative, right, then All right. So these are the 4 steps that for the the discrete case, right? So once again, step one is the likelihood function. Step 2, you take the log. Step 3, you take the derivative with respect to theta and set to 0. And step 4, you take the second order derivative and show that the second order derivative is negative at the solution for star. And if it is negative, then theta hat is a MLE, or maximum likelihood estimated, right? So this in the discrete case, right? There's no need to copy this down. As you know, I will post things online as soon as the class is over. Now, before I do some examples, I need to, because I talked to some of you seem to be rusty about mathematics. I mean, this is not a course. This is not a course in mathematics. This is a course in statistics, as in, right? But I mean, looking at the quizzes, I need to introduce you to some elementary math. I mean, don't get me wrong. I know a lot of you here, they're experts in math, probably more than me. You probably know a lot of things. All right, shh. Listen, guys, please. You should have, number 1, you should have a sum, I from 1 to n, of c. C is the constant. What is that? C equal to n times the constant, right? I'm sure you know that. Yeah? And you should have something like all right, if you have this, you can write this as a constant times the sum of, because I mean the reason I'm giving you this is because I've been teaching for the last 10 years. I've been teaching a second year course called Statistical Methods. I think you'll be taking that course next year. I mean, a lot of students in that course don't know the simple identities like this. Okay, that's the reason I'm giving you this, right? And you should have, say, for example, squared, right? Come on, guys, are you okay? Is it too simple for some of you? Yeah? Yeah. You can write this as the sum right? You can write this like this, yeah? All right, you can also write it like this plus right. All right, these are two ways of writing this, right? So these are 3 identities involving sums. Okay, try to remember them if you can, right? Now, next page. Now I want to give some more identities. Shh. You guys okay? Right, these are identities involving products, right? Now, if you have something like this, a product of a constant from 1 to n, what do you think is equal to? It's the nth power of c, constant, right? Okay? And number 2, if you have a product like this, product of two terms, a constant times, this is a constant times xi, this is all right, this is c, the constant power n times the product of xi, right? All right, number 3, if you have something like this, the product of e, you know the e term, right, the exponential, e of cxi is the same as this. You've seen this before? Yes? Okay. Seems some of you have all seen everything before. All right? Okay. And number 4, if you have e c xi power, say, alpha is a constant, right? Then this you can write as e c, the sum like this, right? And number 5, if you have a log of a product I from 1 to n of xi, then this is the same as the sum. This is what I was just saying a minute ago, that the log of a product is the same as the sum of the logs, right? So these are some 5 identities involving products, right? You may want to, I mean, I'm sure most of you know this, I think. Maybe some of you don't know, I don't know. Yeah? Okay. Okay. Anyway, the next thing, okay, now, as I did last week, you know, I'm going to do 10 examples. I'm going to do 10 examples on MLE, right? So don't tell me that I haven't done enough examples. Okay? right? Shh. Right, you have a random sample from an exponential distribution. I'm sure all of you know this distribution with parameter A. Okay, and we want to find the MLE of A, right? So what's the first step, guys? The first step is to write down the likelihood function of A, right? Which will be the product I from 1 to n of what's the density of the exponential? All right, now using the rules that I just mentioned, I mean, I listed quite a few identities. Now, what would this simplify to? This would simplify to a power n okay. All right, so this is what you get. All right, this is the likelihood function. You with me or not? All right. The second step is to take the log likelihood function okay, so this is the log of the likelihood function. Step number 3 is to take the derivative with respect to A. So you get n okay. This is what you get. Set this to 0. Now, if you solve this equation for A, you get A hat being the estimator for A, equal to n divided by the sum of xi, right, which is 1 divided by the sample mean. Okay? Remember, the sample mean is the sum of xi divided by n. Okay? Step number 4. Okay, in order to make sure that this is an MLE, we need to find the second order derivative, right? So it's going to be the second order, so that's the first order derivative of this, which is minus n by a squared, which is negative, right? Because anything squared is a positive number, right? Hence, right? Is that clear, guys? Any questions on this? Are you okay with this or no? Yes? You're right. Don't just look at me, guys. Just say, are you okay with this? Yeah. Yes. Yeah. All right. Yeah. All right. All right. That's example 1. Example 2. All right. Now, here we have a random sample from a Poisson distribution with parameter A, right? And we want to find the MLE of A, right? Now, Poisson is a discrete distribution, as you know. All right? So it's different from the first example. Now, what's the probability mass function of the Poisson? Let me check. Let me check how many of you remember. Yes? Like that. You can draw it with your pen. Yeah? All right? All right, this is where, okay, to simplify this, you need to use the identities that I just mentioned a few minutes ago, right? So if you simplify this, what do you get, guys? You get E minus NA, A power xi, and the product of xi factorial I from 1 to n. Okay, so this is, I mean, I've seen many cases where people can't go from this line to this line. I mean, this is a second year course, I'm not talking about first years, this second year course, where you can't get this step right. So you have to, I mean, that's why I gave you these identities, the identities for the sums and the identities for the products. Okay, make sure you remember those identities. And when you go to your second year, make sure that you do this correctly, right? Okay? Right. Now, if you take the log of this, you listen please, if you take the log of this, you get minus NA plus all right, so this is the log of the likelihood function, right? And the next step is to differentiate the log likelihood with respect to A. So you get minus n okay, and the derivative of log A is 1 over A, as you know. All right, set this to 0 and solve for A. You get A hat equals to 1 over n times the sum of xi, which is the sample mean. Okay. Now step number 4. Now to make sure that this is an MLE, we need to find the second order derivative. Okay, which is, if you differentiate this one more time, you get minus and this will be negative because this will be negative unless all the xi's are equal to 0, which is unlikely to happen, right? Because I mean, you cannot. I mean, if you generate a data that follows the Poisson distribution, it's very unlikely that all the data will be equal to 0. Because remember, the Poisson distribution is defined from 0, 1, 2, etc. Right? Okay. Okay. So hence, Right, hence it's an MLE. Yes? Any questions so far? No? Yes? All right, example 2. Now, example 3. And you listen, guys, please. Example 3 is this. You have a random sample from a normal distribution with mean equal to theta and variance equal to 1. Okay? Find the MLE of theta. So step 1, I mean, you guys remember the density of the normal distribution, right? Anybody here who doesn't remember the density for the normal? Okay, this is the density of the normal distribution with mean theta and variance equal to 1, right? So if you simplify this, this is what you get. Okay? So that's step 1. Step 2 is to take the log. Right? Right, this is step 2. Step 3 is to take the derivative Now, let me. I know you guys are doing calculus. What's the derivative of this with respect to theta? You don't know? I'm sure. This is a constant, so the derivative is 0, right? And what's the derivative of this with respect to theta? 2 times and the derivative of minus theta with respect to theta is minus. I use the chain rule. I'm sure you know what the chain rule is. Don't tell me you don't know what it is. Yeah? Okay. So this is what you get, right? And this, if you simplify this, you get sum yes? Okay. And if you take the sum inside the brackets, you get 2 sums, right? Sum of xi minus the sum of theta. So this is sum of xi. The sum of theta is, I just mentioned, is n theta. Set this to 0, right? And the solution you get for theta hat is 1 over n times the sum of xi, all right, which is x bar. All right, so the solution for the equation is x bar. Now, to make sure that this is an MLE, we need to do step 4. The second order derivative of this one with respect to theta is minus n, which is of course negative all the time, right? And hence, all right, hence theta hat equal to the sample mean is an MLE. All right? Is that clear, guys? Yes? All right. Now, so that's example 3. Example 4. Shh. Just calm down, guys. Right here, you have a random sample from a normal distribution with 0 mean and variance theta squared, right? Listen, guys, please. Right? So this is the density. You're taking the product of the density from 1 to n. So you do that, you get oh, it's raining outside. Is it? Oh, man. All right, this is what you get. Okay? Okay? Step 2, you take the log of the likelihood, right? Right? Step 3, take the derivative with respect to theta. It's going to be minus n over theta. And the derivative of this with respect to theta is plus 1 over theta cube. Right, set this to 0. you get if you solve this equation, you get theta squared equal to 1 over n times the sum of this. So theta is equal to the square root of 1 over n is actually plus or minus the square root. Remember. Now, let me ask you, this is a simple question. I'll be disappointed if you don't give me the right answer. Now, I'm saying that theta squared is this, so theta is plus or minus. Now, so you have two roots, plus or minus. Which one of them is valid? Or are they both valid? Huh? Come on, guys. Are both roots valid? Huh? Come on. You're not thinking, guys. Now, what does theta represent? What does theta represent? Huh? Theta represents what? Look at the question here, guys. You have a random sample from a normal distribution with 0 mean and variance sigma squared, right? So theta represents the standard deviation, right? Standard deviation by definition must be positive. It cannot be a negative number, right? Standard deviation. So the only possible root is the plus root. The minus root cannot be a valid root because standard deviation must be a positive number by definition, right? All right, number 4. If you differentiate this one more time with respect to theta, you get n over theta squared minus 3 over theta power 4 times the sum of xi squared. Now we need to show that this guy is negative. How do we do that? Okay, we need to show that this guy is a negative number, right? So okay, are you with me? Now we know that theta hat squared is equal to 1 over n times Okay. Are you following me or what? We just showed you previously in the previous slide that theta hat squared is equal to 1 over n times the sum of xi squared. So the n and the n cancels, this guy and this guy cancel, so you get minus 2n over, right? Which is of course a negative number, right? You follow me, right? Hence, all right. You okay, guys? Any questions on this? Yes? You guys okay? Yes or no? Okay. All right. Now, I'm going to give you one more example, but I'm going to ask you to think about it before you come on Thursday. So don't be ready to leave yet. You're always in a hurry to go. This is example 5. Shh. Right. This example will really make you think, right? Because this is where you have a random sample from a normal distribution with mean equal to theta and the variance equal to theta squared. Right? Try and see if you can do it before Thursday. I will show you on Thursday. Right? Okay, guys? It's what? Okay, it's all right. Thank you. Well, you're late all the time. The deadline was 3 o'clock. It's okay, yeah. It's a way of constructing point estimators.
Okay. Are they always unbiased? Or?
No, they're not always unbiased. But they are always consistent.
Okay.
They are always consistent, but they are not always unbiased. But they are always asymptotically unbiased.
No, right.
Asymptotically unbiased and consistent. So it's generally people use MLE for constructing point estimators.
Excuse me, do you have a lecture now here?
Yeah.
From 4 to 5?
Yeah.
Oh, okay. Sir? Okay. Are you lecturing here? Sorry.
Please don't turn it off.
Yes, no,
Okay.
I was trying to check if there is a... Are you going to use
I am.
PC?
Yes. Yeah. Is that okay? Yeah. You were trying. What were you trying to check?
Do you have... If you connect, can we check if Excel, the
Sure.
solver
Yeah. No.
in
No.
Excel
Help
is
yourself.
installed?
Yeah.
I'm lecturing here tomorrow morning and
Oh, I see. Okay.
I have to tell IT to install it's a plugin for
Oh,
Excel.
I understand. Yeah. Yeah.
I
Somebody,
guess
are these your glasses?
No.
No. A pair of glasses down here. I don't know if anybody needs them. Right. Let me see them. Okay. So it'll be my username though.
I think if it's installed, it should be installed for everyone.
Yeah. He's absolutely throwing it down. I'm soaking wet. I thought it was going to be late, and now I've
There won't
been
be a
soaking wet.
lecture so late.
I know, it's terrible.
By the way, I'm Manuel.
Okay, I'm Jo. Hi,
in the
nice to
business
meet you. Oh, I'm in biological sciences. So
Biological
SPMH,
sciences?
yeah. Right, yeah, help yourself, have a look.
So, could you just open it? So
Yeah, I've done it so upside down. Programs here, do you want to try?